Okay, we're continuing with the book. This is part 14, Prevent and Reverse Kidney Disease. We're going to be talking about atherosclerosis and Dr Sloop. We're on page 71 if anybody's following around in the book. He's one of the great pioneers of atherosclerosis research, and he really developed a deeper understanding of what's called atherothrombosis theory, which is really a fancy way of saying atherosclerosis is due to a thrombosis, a blood clot. He showed that LDL cholesterol functions as a bridging molecule and sticks the red blood cells together. So if this was, if my two fists are a red blood cell, the yellow would be LDL cholesterol sticking them together. It overcomes the zeta potential, the negative charge on the outer surface of the red cell, and sticks them together. LDL cholesterol does that, chylomicrons do that, triglycerides do that. So that's why high-fat diets are bad. They're prothrombotic. They also cause hypertension because they stick the red blood cells together. They make your blood thicker. The reason you have a blood pressure is to pump blood to the top of your brain, your cerebral cortex, against gravity. If you're pumping thick blood, normal blood's like water. If you're pumping thick blood like a milkshake, pressure has to go up. If you eat a lot of sodium, you vasoconstrict. Now you're pumping thick blood through a constricted system. Pressure has to go up more. Classic, high-fat, high-sodium meal would be like eating a pizza. Okay, he's got lectures on the internet. You can watch him himself lecture. Dr Sloop. Just type in the importance of blood viscosity or measuring blood viscosity. I'll show you his book here. This is his book, Blood Viscosity: Its Role in Cardiovascular Pathophysiology and Hematology. It's a great book. I learned a lot from it because I had been trying to understand atherosclerosis. I had a background being an imaging-guided surgeon, vascular interventional radiologist. Trained at Harvard, with a deep interest in atherosclerosis, doing tons of arteriograms, angioplasty, stenting, thrombolysis, all that stuff. And I thought I understood atherosclerosis pretty well, but then I learned, no, the pathologists understand it better because they're always looking at it under a microscope, and it's a blood clot. And then I went back and looked at all these CT angiograms, MRA, MR angiograms, catheter angiograms, and yeah, it's a blood clot. Okay, you can't tell the two apart because they're the same thing. Okay, so anyways, Sloop did a great job with that. In every work of genius, we recognize our own rejected thoughts. They come back to us with a certain alienated majesty. Yeah, I had noticed a long time ago that I couldn't tell the difference between atherosclerosis and a blood clot, but I hadn't given it a lot of thought. So here's a paper by Dr. Sloop. Atherothrombosis is a thrombotic, not an inflammatory disease. He actually thinks elevated C-reactive protein is more an issue of it functioning as an indicator of muscle glycogen being depleted rather than of inflammation, so to speak. He says he doesn't see that much inflammation in the arteries themselves, more of just an organized hematoma, the immune system coming in to clean up the clot. Let's see here. So that's one of his papers on it. Here's an idea of the zeta potential, that red blood cells have a negative charge on their outer surface called the zeta potential. It's due to the sialic acids at the end of the glycocalyx. It's due to primarily the repeating disaccharides like the heparan sulfate. Sulfate's a lot of negative charge on the glycocalyx, the coating of the outer surface of a red blood cell. And all the blood cells have it. All the white blood cells have it. All the endothelial cells have it. They all have a zeta potential, a negative charge. Even the plasma protein, albumin, has a negative charge. So they don't stick together. It makes sense. It's brilliant. There's a lot more stuff God designed into the human body and life in general with electrical charges than is recognized by conventional medicine. Conventional medicine, it knows that there's an EKG for the electricity of the heart. It knows there's an EEG, the electricity of the brain, but it simply doesn't pay attention to it with regard to blood cells. But it's a major issue in blood cells. So here's a bridging molecule, things that can stick it together. IgM antibodies, LDL cholesterol, fibrinogen clotting protein, uric acid. Okay, and then if you make blood thrombose, you activate the platelets, which you can do with high salt diets. If you activate the fibrinogen, you have it undergo an amyloid transformation due to LPS, LTA, bacterial endotoxins, or excessive free iron. That'll all predispose to clotting. Here's LDL cholesterol. The higher the LDL cholesterol, the thicker the blood, the more higher the blood viscosity, and that's going to lead to more hypertension. I made longer videos as a tribute to Dr. Sloop. Typical red blood cell is about 7 microns in diameter. Capillary is only 5 microns, so their RBC is bigger, so it has to deform itself to flow through a capillary. Okay, it can fold back on itself. It's normally quite flexible. Red blood cells live about 120 days. That's because as they get older, they get more stiffer. It has phosphatidylserine externalization, meaning from the inner leaflet of the plasma membrane to the outer leaflet, it flips and it becomes more stiff. They also get more glycated, like hemoglobin A1C, and then they can't go through the filters in the spleen, like 3 micron diameter filters, so they get removed. Typically, the life of a red blood cell is about 120 days. Okay, that's another example of the bridging molecules causing a rouleau formation, sac of coins in French, and when the red blood cells are stuck together, it's harder for them to get through the capillary. You have to push them with higher pressure. Okay, so that's just a brief thing. I have a lot more information about Sloop and all his theories and stuff in my lectures about him and about atherosclerosis, but I was just kind of making the point that high-fat, high-sodium diets are bad for atherosclerosis, and we're talking about the kidney. The book's about the kidney, so if you cause atherosclerosis in the arteries of the kidney, then you can't perfuse the kidney adequately, and it's not going to be able to do its job to filter blood. And if you cause hypertension, that accelerates atherosclerosis formation for reasons I've talked about elsewhere about hypertension being prothrombotic because it decreases blood flow patterns. It causes more turbulent, chaotic flow at bifurcations and more retrograde eddy currents that the endothelium perceives as vascular injury, and it sheds its antithrombotic glycocalyx, a 600 nanometer high component, whereas the residual 60 nanometer high vascular cell adhesion molecule and other adhesive molecules remain present, and clots start forming, and you gradually occlude the vessels. It causes atherosclerosis. So anyways, Sloop's telling you the truth. That's what you need to know to help prevent atherosclerosis. That's what basically Caldwell-Esselstyn did and others who've treated patients with low-fat vegan diets to prevent atherosclerosis. So I hope you found that helpful.